Today we are going to discuss the test of significance called the analysis of variance, often abbreviated as Anova. An easy way to think of Anova is as an extension of the t-test for the significance of the difference between two sample means. However, Anova goes one step further, for it is only appropriate for comparing 3 or more categories or samples of an independent variable. For instance, Anova is useful in comparing potential differences between marital status. There is a 5-step process associated with the test of significance for Anova. It is similar to the 5-step test for a hypothesis involving either one sample case or 2. Our research question for this exercise is there a significant difference in the average income amongst the provinces? Sure. The following formulas will be associated with this version. Although it seems like this test for the significance will be used to analyze the difference between sample means, the computational routine for Anova requires us to analyze variance by developing 2 separate estimates of the population variance, hence the name. Remember, variance is a measure of dispersion. Our first estimate of the population variance is based on the amount of variation between each of the categories, or in this case provinces, and the other is based on the amount of variance within categories. Before we construct these estimates, we need to learn a new concept called the total sum of squares, or SST. SST is the measure of the total variation of the scores. To construct the 2 separate estimates of the population variance, we divide SST into 2 components. The first one reflects the pattern of variation between the categories, and it is called the sum of squares between, or SSB. This will tell us the variation of income between the provinces. This is what we are most interested in. The second component is based on the variation within the categories, and it is called the sum of squares within, or SSW. This will tell us the variation of the income within the provinces. The first step is to make assumptions and meet the test requirements. Anova has 4 strict requirements. The samples must be independent and random. We can assume we have met this requirement as we have gathered our data from the 2006 census undertaken by Statistics Canada. The level of measurement must be interval ratio. We are dealing with income, which is an interval ratio variable. Populations are normally distributed. Population variances are equal. With these last 2 requirements, as long as the sample sizes are large enough and relatively equal, Anova can tolerate some violations of these latter assumptions. If they are not nearly equal, you should not be using Anova. The second step is to state the null hypothesis. For Anova, the null hypothesis always states that the means of the populations from which the samples were drawn from are equal. In other words, the null hypothesis would state that the average income from each province would be equal. Note that this null hypothesis is exactly the same as the null hypothesis for the 2 sample t-tests, just with more samples. Remember, we are not asking if there are any differences between the samples, but rather if the differences in income between provinces are large enough to reject the null hypothesis and justify the conclusion that the differences exist and are significant. Thus, our research hypothesis states that at least one of the population categories and their means will be different. We hypothesize that one's location in terms of province will produce a difference in income. The third step is to select the sampling distribution and establish the critical region. We have no choice but to use the F distribution for Anova, which is summarized in Appendix D of the textbook. There are 2 separate columns for an alpha level of 0.05 and 0.01. We will be using an alpha level of 0.05 as per convention in social sciences. The F distribution is similar to the T distribution associated with the 2 sample hypothesis test, as the value of the critical F score will vary by degrees of freedom. After completing the formulas needed to acquire SST, SSB, and SSW, we need to calculate the degrees of freedom. There is a separate formula for each type of square estimate. Once you have calculated these degrees of freedom, the numbers at the top of the table are the degrees associated with the sum of squares between, which are the degrees between estimate, or DFB. The numbers down the side of the table are for the sum of squares within, the degrees within, or DFW. You first go to the top of your table with your DFB, and then go down the table until you see the degree associated with your DFW. This number between the 2 is your F critical. We used SPSS to calculate our DFB and DFW. We used these degrees to find our F critical in Appendix D in the back of the textbook. We found our F critical to be 2.21. Remember, Anova is a one-tailed test, which is why all of the values are greater than 1. We are only concerned with the outcomes in which there is more variance between categories of the independent variable, or in this case provinces, as we are interested in seeing how the independent variable impacts our dependent variable of income. The fourth step is to compute the test statistic. We must use the degrees of freedom, DFB and DFW in this case. We are interested in constructing the mean square estimates to the population variance. First, we compute the mean square within. Second, we compute the between estimate. Once we have these numbers, we compute the F obtained. SPSS calculates this for us, and since the purpose of this video is to demonstrate SPSS output, we will use SPSS's calculation. Our F obtained is approximately 0.826. The fifth step is to make a decision and interpret the results of the test. We will now transition to SPSS to discuss our interpretations related to the potential difference in income depending upon one's location in terms of province.
We will be using the shortened version of the 2006 census. We will be specifically analyzing the variables of total income, or TONT Inc., found in column 32, and the provinces. For Anova to work, we must establish equal population variances, as it is one of our assumptions. We can do this by equalizing our sample sizes. This will require collapsing some provinces into regions to equate other provinces with larger populations. To do this, we must click Transform and then recode with different variables. Find PR or province and click the arrow to place it within the Input-Output variable box. In the Output variable box, we will write region into the name and label text boxes so we can locate our collapsed samples later on when we compute Anova. Change the name and then click on the old and new value box. From this point on, Chapter 9 of the textbook provides us with a way to do this on page 266. This process involves changing and combining the old numerical values of the provinces to new numerical values in order to allow one to combine the provinces together to form equalized regions. Because the textbook outlines this process, and for the sake of time, we will not go through each individual transformation. Number 1 will represent Newfoundland and Labrador in the new data set, along with Prince Edward Island and Nova Scotia and New Brunswick. Number 2 will represent Quebec. Number 3 will represent Ontario. Number 4 will represent Manitoba and Saskatchewan. Number 5 will represent Alberta, and number 6 will represent British Columbia. SPSS will execute the transformation necessary to establish our sample cases as relatively equal in terms of both their size and variance. To use SPSS to compute the one-way Anova procedure, we must click Analyze and then Compare Means and then One-Way Anova. The one-way Anova window will appear. Find total income in the variable list on the left and click the arrow to move the variable name into the dependent list. Now find our new variable, the regions, and then click the arrow to move the variable into the factor box. We are going to request that SPSS also provide us with information on the means and the standard deviations of the data along with Anova. To do this, click Options, then click the checkbox next to the word Descriptive in the Statistics option. Then click Continue, then OK, and the output will be produced. The Descriptives report demonstrates our summary statistics. The mean demonstrates the average income per region. We can see that according to this statistic, Alberta possesses the highest average income, whereas Manitoba and Saskatchewan possess the lowest. The means may look different to one another, but Anova will help us determine if the difference in the means is statistically significant or just an occurrence of chance or statistical error. The standard deviation here demonstrates to us the dispersion of income within each region. When we look at the Anova chart, we can see that SPSS calculated the sum of squares total, the sum of squares between groups, and the sum of squares within groups. The sum of squares total refers to the total variation of all income scores we have received in this dataset. The sum of squares between refers to the total variation of scores between the provinces in terms of income, and the sum of squares within refers to the total variation in income within each individual region. SPSS also calculates our degrees of freedom, which we use to construct our F-critical. By using Appendix D, we found our F-critical to be 2.21. Remember, our null hypothesis is that the average income is equal amongst the provinces. SPSS calculated our F obtained, which is 0.826. Because our F obtained 0.826 falls within the critical region of 2.21 and does not exceed it, we fail to reject our null hypothesis. If our F obtained was higher than 2.21, we would be able to successfully reject our null hypothesis. In other words, Anova is telling us that there is no statistically significant difference amongst the provinces in terms of average income. This requires us to now assume that the variation we observed earlier in the sample mean incomes is insignificant, as stated in the textbook. Before we analyze SIG, remember that our alpha level is 0.05. SIG measures the p-value, or the probability of getting this data if the null hypothesis were true. Now, if SIG is equal to or smaller than alpha, it suggests that the observed data is inconsistent with the assumption that the null hypothesis is true and that it should be rejected because there is a significant statistical difference. In other words, the statistical difference would thus be significant if the null hypothesis were true, because then the probability of obtaining data on a difference in income as a result of error or chance would be equal to or less than 5%. However, in our case, our SIG is 0.531, and thus much over our alpha level of 0.05. Thus, the probability that this difference in income is due to chance or error is 0.531, or in other words, there's a 53% chance that this particular data set of difference is due to either chance or error. The appeared difference in income is not significant. This difference is a greater chance at being an error or a random probability rather than being a realistic significant difference. Because there is a great chance that this difference in income is an error of this nature, we must fail to reject the null hypothesis. Ultimately, what Anova is showing us is that the average income levels amongst provinces is relatively the same. We can also use an error bar graph to get an indication of which means are different or if they are not. In this case, we have established that there is no difference. To produce an error bar graph, click Graphs, Legacy Dialogues, and then Error Bar. The error bar dialog will come up and you click Simple and then click Summaries for Groups of Cases. Then click Define. Place total income in the variable box and then region in the category axis box, and then click OK to produce your error bar graph. By eyeballing this graph, we can see that all of the confidence intervals overlap entirely with one another, as they are all relatively beside each other. This once again shows us that income levels may be similar to one another within all provinces. Although Anova is useful, for it can tell us that a difference may exist or it may not exist in regards to income or another variable of choice, Anova cannot identify which mean or means are significantly different. Thus, if one did find a difference in income amongst the provinces, Anova would be unable to tell us which means are different. Anova simply tells us that there is a difference. We need to utilize more complex statistics in order to delve into this difference. Anova is also prone to both type 1 or alpha error and type 2 or beta error, as covered in Chapter 7 of the textbook. It is important to keep these limitations in mind when computing Anova as your test statistic of choice. This concludes our presentation on the analysis of variance.